Well, in this video, we're going to look at chapter 4 again. This is video 2 for chapter 4. We're looking at the control of metabolic reactions, particularly enzymes, these amazing molecules. So in this, we're looking at how things are controlled. Now, all cells, as it says here, perform both catabolic, breaking down, and anabolic, building up. Catabolic releases energy. Anabolic requires or absorbs energy. But these rates of these chemical reactions are very carefully controlled. Our body doesn't just want our chemistry inside of it to just happen just because. We want to have a reason, so we control it. And so the way we control it is through these things called enzymes. And so different cells will produce different enzymes because they all have specialized metabolic processes. Things in the kidneys have to do different things than things in the brain, and things in the liver have to do different things than the things in your eye. So there's all kinds of enzymes each individual cell will be programmed to use. And so these enzymes, as it says, greatly increase the reaction rates. And you'll see in just a second. So enzymes, remember, enzymes are proteins, and if we were in a chemistry setting, these enzymes would be called catalysts. So if you've ever taken chemistry, you've probably heard them more often called catalysts. They're very large proteins, and again, remember, proteins have a very specific design, a very specific shape. We looked at this back in I want to say it's chapter 2, when we were looking at the proteins. We said they had a 4-layer orientation. You had primary, secondary, tertiary, and quaternary. The tertiary was how the entire enzyme or the entire protein looked. And we said the quaternary is how it interacts with other proteins, and that's where we get into this idea of these enzymes. Now, as it says, it increases the rate of reaction. So just imagine if I have a whole bunch of little molecules in this room, and they're all moving around randomly. And so if I say, I've got this area, and they're all moving in different directions, and occasionally they bump into each other as they're going around. But let's say I have a molecule that's kind of like this, and I've got this one little like hydrogen here, all right, and then I've got another molecule that looks like this, and over here it's got a hydroxyl group. Now these molecules might bump into each other occasionally, but it has to get where this bumps directly into this for the bonding to happen to make a molecule. So the odds of all of these that are in here bumping into each other just right at the time we need it is really, really low. And we call that activation energy. And so if I if I take and put a little flame underneath here, these will move faster, so the odds increase, but they're still astronomical. And so what our body does is we control all of these reactions by producing a special molecule that is called an enzyme. And it is designed, it'll have a little seed in it that's designed perfectly for molecule A over here and molecule B, so that they sit in it in a way that these two bonds are forced to be right next to each other. And in doing that, we say that it lowers the activation energy. So the activation energy would be how much energy would be needed to make this happen. If this was left to its own, you're almost talking about infinite. You'd have to really get these things moving and just hope. But once we release an enzyme, the reaction's going to happen, because the enzyme is set to grab both of these molecules and really force it to happen. And they're not destroyed during the reaction, so they can be used repeatedly. And they only act on certain molecules. We call those molecules substrates. So if I say this is enzyme X that I drew here, it only works on molecule A and molecule B. It does not work on anything else. So those are substrates. And so It's got the ability to recognize the substrate. The ability to recognize the substrate depends on the shape of the active site of the enzyme. This little part here that I said is the perfect little spot to fit these two molecules in, this little couch that's only made for those two tushies, that's called the active site. And so we're going to look in the course of 210 and 211, and especially in 211, you're going to look at a lot of different enzymes, and just understand that enzymes generally end in ASE. In the digestive system in particular, you're going to see a bunch of them. And so lipids, for instance, in order to break down lipids, we produce enzymes, and generally they're going to be referred to as lipase, right, with that ASE end of it. There's a sugar called sucrose, and we need to produce sucrase to break it down. One of the ones that most people would know is lactose, which is a milk sugar. We have to produce lactase in order to break it down, and a lot of people don't. So this is how enzymes work. Now this little picture is kind of showing it. It's probably better than mine, I get it. But this is A and this is B. I don't know, I always fall for trying to write on this. But anyway, those two are the substrate molecules. This is the active site. They bind into it. It forces them to get together, and I have made a larger molecule. And what's going to happen here, as these get together, water is going to be removed, right? So that's dehydration synthesis, because we have removed water and made this molecule. On the flip side, it's also a reversible reaction, so I can put this product, which would now be the substrate, in here. I will force it to where it holds still so water could get into it, hydrolysis, break it down, and then now these would be two product molecules. And that going this way is the sign of catabolism or decomposition. Now, most of the things in our body aren't as simple as A plus B equals AB. They're usually pretty long processes. One of the ones we'll see, one of the many ones, but one of the ones we'll kind of pay attention to in this chapter is called the citric acid cycle. It is a whole step of chemical reactions that are controlled by various enzymes, and so it's a pretty amazing thing, but it's called a metabolic pathway. And in this, the very first step in general is called the rate limiting step, and the enzyme that makes it happen is called the rate limiting enzyme, which means that all of these things are just hanging out, and I'm going to get things started by this first reaction. And again, we call that first reaction the rate limiting reaction, and it's controlled by the rate limiting enzyme. Now, most of these pathways by far are controlled by what we call negative feedback. And just remember, so all it's saying is I got a set point, and my body needs, let's say, hormone A, and I start getting low on hormone A. My body will produce the rate limiting enzyme to cause the creation of the hormone A. So I start making it, and it goes up, and then I'm going to make to where I have enough. And then I'm going to stop making that rate limiting enzyme, and I'll start using hormone A, and I'll start going down where I don't have enough. And so we go in this little cycle, and we call this negative feedback. This is an example of a metabolic pathway. And again, we'll see that a lot of times, we're not going to really get into this. This is more biochem, but this is basically how things work. And the only thing, I'm not going to test you on this other than it's a metabolic pathway, but just understand that the things that happen in your body are so much more complicated than we tend to think. I mean, most things that are happening are very complicated chemistry processes. And so enzymes will have helpers. Sometimes we call them cofactors and coenzymes. Now, a cofactor in general is what we first looked at as an ion. Now, this term ion has had a lot of different name changes just in these first couple of chapters. Remember, an ion is just a charged atom. And then we talked about them, but then we looked at ionic bonds. But if an ionic bonded molecule gets put in water, it's dissociated into its electrolytes. So ions are electrolytes. Then we looked at the non-organic molecules, and we found out that inorganic salts are another way to say the same thing. So ions are electrolytes, are inorganic salts, and I've got another one for you, and it's not on here. They're minerals. All right, they're also called minerals. I shouldn't fall for it because I just want to do it. Doggone it. Minerals. Yay! And I probably misspelled it because I'm trying to make it where it's legible. But anyway, cofactors are minerals. And in dietary world, that's kind of how we hear it. The other one is coenzymes. Coenzymes are vitamins. Now, coenzymes, basically the difference between the two is coenzymes are organic and cofactors are non-organic. Again, minerals, ions, electrolytes. So we're talking about things like sodium, potassium, calcium, the iron. These are examples of cofactors. Coenzymes are like vitamin C. So immunity, there are enzymes that help our immune process. And for instance, iodine or zinc. Zinc is a very important cofactor for some enzymes that help our immune system work. The coenzymes, vitamin C, does the same thing on the vitamin side. Now, when I was a little kid, I would have used, if I'd have known this, I would have used this to make my mother understand that Cap'n Crunch is a very important breakfast cereal because it's packed with vitamins and minerals. Yeah, no, but I know my mom wouldn't have fell for it, but I would have tried. So anyway, cofactors are these minerals that help enzymes function. Coenzymes are vitamins that help them function. Now, one of the really important things, we'll talk about it a little bit at other times, is this term denaturation or denaturing. Enzymes, because they are proteins and they have a very specific tertiary shape, the way they look, if something happens to them, particularly pH changes, but it could be heat and chemicals, radiation, if anything causes it to change the shape, it is referred to as that has been denatured, or the process is called denaturation. And since we have that very specific active site on an enzyme, if it changes the shape, it will not work. And a denatured protein cannot be used. And that becomes a real problem. So, when I say a real problem, I mean like death. So anyway, this is an idea of or how these are controlled. And again, enzymes are the main thing. And remember, enzymes are proteins that have a very specific shape. And we call that certain spot the active site that's going to bind to the substrates. All right, I hope that all made sense, and have a great day.